But everybody's got an opinion. Okay, we'll see how the world progresses. I'm going to guess it's going to be a lot the same, but we'll see. Okay, let's come back to the central limit theorem. I need to piece together a lot of different things to make this proof that we're doing. This is the same proof that's presented in the book, so let's just walk through the details slowly. I started presenting on Taylor expansions without any context last time. I just started doing it. So just to remind us of things. So we're going to build in all the context and show what we're trying to do with everything. And we'll talk about the steps of the proof and what's important. So what our assumptions are and where we're using those assumptions. So the central limit theorem says this right here. So for IID data, and there are other forms of this that don't require IID-ness, this statistic, so this standardized X bar, that's X bar. Subtract off the mean, divide by the standard error, it converges to a normal 0, 1. And that's true for any distribution so long as it has a finite variance. So things like Cauchy's, this wouldn't apply to. Does anybody know if you take a Cauchy 0, 1? So just, here's a fact. I'll say Z comes from Cauchy. They kind of look like normals, but they're not. They're very heavy-tailed versions. I'll say 0 or 1, just to plug in some parameters, but this will change to any location and any scale. If I end up looking at some of the ZI's over, I'll say N, so I goes from 1 to N, does anybody know what this statistic converges to? So Z bar. Just curious if you know. It's a Cauchy. It's a Cauchy back. And it's true for any N. So it's going to be a Cauchy. Anybody know which Cauchy it is? Probably isn't going to change the scale or the location. So I think we could figure that out. But it might be a little bit harder to figure out this other part. Anybody have any guesses? It's 1. It doesn't change the distribution. So there's these little outliers in the tails that we'll see, and it always ends up pulling that Z-bar around. So it never actually converges to a point. So for this thing, if I have a finite variance, which Cauchys don't, is they're going to converge to a normal distribution, and the scale's going to be getting tighter and tighter and tighter. So we cut down on our uncertainty when we apply the CLT. So it's kind of a cool thing that this is always true. I find it remarkable that this is true. So I wouldn't have guessed that, but since I'm so familiar with it, I'm comfortable with this idea. Let's see if we can prove it. We're gonna do probably one of the easier proofs out there, but it's not trivial. What's going on? So we're gonna do a proof where we're gonna just say that this thing converges to a normal 0, 1 in distribution. So we're not going to say anything about the fashion in which it converges. So I'm not going to say anything about whether or not it converges and it gets, it starts converging to this thing and it never jumps far away from it. Something like that. There are almost short proofs on the CLT, but it's not always true. So you need other conditions to show that the CLT converges to a normal 0, 1 in an almost short fashion. So it's not true in general. I used to believe that that was true, that it converged in the strongest sense. That's not always true. Saying that for a statistician, if I'm just going to compute a probability, this is good enough, just knowing which distribution it is. I can measure probabilities on it, and I can answer questions with it. So if you want to know forms of convergence for this, there's plenty of papers out there. It's pretty modern research. But that would be a more mathematical question, a curiosity. So, which is fair game. But in terms of applying everything to an actual application or problem, just saying that it converges in distribution, I think it's a strong enough statement. We're also going to make our lives a little bit easier so that we don't have a 20 chalkboard proof. And this assumption will do it. So it's going to have, we're going to consider distributions with smooth moment generating functions, where the moment generating function is this thing right here. I usually call that MYT. the moment generating function. It's also known as a Laplace transform. So exactly the same thing. This is not required for the central limit theorem. We don't need that condition, but it's going to make the math easier. So what I'm basically saying is I can express the moment generating function with the Taylor expansion. So our assumption is that these derivatives exist in the first place. We don't absolutely need that to be true. All we need for the central limit theorem to hold is that it has finite variance. But it's kind of hard to just talk about arbitrary functions, just any old function right here. I'm going to make some statements, but I'm going to encode in this assumption into the Taylor expansion. So we're going to use this assumption in the Taylor expansion explicitly. If you don't like that and you want to do things, if you want to show the CLT for distributions where the M.G.F doesn't exist, you can use a Fourier transform and just kind of supplement it. I'm not going to test you on any of that. I don't think we know enough about complex numbers in this class, but there is a very similar proof to the one that I'm going to show you. It's a little bit more general. The proofs that I've seen that only require this assumption are rather long. So we won't study that. Okay, any questions about what we're going to try to do? So we're going to try to prove this statement right here. What I'm essentially going to prove is that the M.G.F for this statistic right here, it's going to look very similar to this thing. Except we're going to have mu is 0 right here because it's going to be a centered distribution. So this test statistic right here is centered at 0. So it's going to have mean 0 and it's going to have variance 1. So if I did plug everything into this integral and solve the M.G.F for a normal distribution, it'll be that equation. You can write it down in closed form. I will not require you to know all your M.G.Fs in this class. If you know them, cool. But I personally don't remember my own M.G.Fs, so I have to look them up. I would like you to know this one. So for our case, this is just going to be e to the 1/2 t squared. So the M.G.F for a normal 0, 1 is that function. It'd be cool if you just knew that. If you forget it and I ask you to prove it on a test or a midterm, and you forget what it is, I'll tell you what it is. So you'll need to remind me to remind you. Hopefully we can at least remember that later. Okay, let's go through the steps. Is there a in here? Oh, yeah, this part. Yeah, that's supposed to be X bar. Yeah, very good. This would still be normally distributed, but it would be scaled very strangely if we did that. So, very good. Yeah, that's supposed to be the mean. Okay, I will just point out the way we apply the central limit theorem in practice. We usually do something like this. Applying the CLT is we'll say something like this: x bar n is distributed normal mu sigma squared over n. These are not absolutely equivalent statements. So just because of how we're taking the limit. So I want to pull the ends over to one side of this so that this thing actually converges to something. If I took the limit here, this would go to 0. And so that's not the formally mathematical way, the statement that we're going to prove. But in practice, this is how we apply everything. So you'd use it like this. Just plug everything into that distribution. So, but the central limit theorem does not say this. It says it's approximately true. You might say something about the rate of convergence on all of this. How fast does this converge? It converges as fast as this thing goes down to 0. So this is going towards 0. That's easy to see. This is going towards 0, so it's converging maybe to something finite. How fast is this converging? It converges at the rate in which that goes to 0. And so usually we'll write something down. The rate of convergence is order, this is the notation, n to the minus 1/2, right there. So it converges to a normal distribution as fast as this thing converges to 0. So you'll see people present that sometimes. How fast is that? It's kind of fast. So How does it actually work in real problems? There's a constant out in front of this, and for different problems, there's different constants. So when people tell me about the rates of convergence, personally, I want the constant. I want to know how it actually works in a specific problem, just not a general statement about everything. So I think those constants are super important. How fast does it actually converge? I don't want to know as n goes to infinity how fast it converges. I really want to know if it converged fast enough that I could actually use this thing in practice. And that's a more practical question. So the theory won't tell you that in general. You need to check, and usually we check using a simulation study, something like that. So when I'm going to apply all this stuff, what I usually do is I build a model that looks like what I think generated the data. It's my idea of what generated the data, and then I check in a simulation sense how fast everything's converging, so how fast I think, or I do it to check the appropriateness of that model. Okay, lots of comments. Let's see if we can do this proof. So I'm going to say a few more things about moment generating functions. We know what they are. They're this, right here, Laplace transform if you'd like. And I can make a few statements based off of just the definition of an M.G.F. So let me just write down what we're going to do is we're actually going to solve the M.G.F. for not just some random variable, but some transformation of random variables. We're going to apply the M.G.F. to this thing right here. So this is going to be my test statistic that I'm going to look at. And the test statistic that I'm referring to is based off of these yi's, which are just these centered xi's and rescaled to have variance 1. So you don't have to do this transformation to do this proof. It just simplifies things a little bit. So we're going to be studying the M.G.F. for some of the yi's divided by square root of n. I'll just point out that this thing right here is this thing. They're exactly the same. Let's just show that. So, sum of yi's. Look at what this is. This is just sum I goes from 1 to n, xi minus mu divided by sigma. So I'll just apply my transformation directly. I'll drag my sum in. So this is going to be sum of the xi's. I goes from 1 to n minus n mu. So that gets summed up n times. And then I'm going, oh, this is all right. Divided by sigma. So nothing fancy here. I'm going to re-nickname this thing. Right here, I'm going to call this n times x bar. So exactly the same thing. Bless you. Now I'm going to pull down these n's real quickly. I can rewrite this like this. Just like that. And this almost looks like that, except I'm off by a factor of square root n. So if I multiply this by 1 over square root of n, I'm going to just get this square root of n down here. And this will cancel with one of those, and I'll just have the square root of n. So if you're wondering where that comes from, it's just this sum of the yi's divided by square root n is just that standardized x bar. So exactly the same thing. I'll point out that this M.G.F. can be re-expressed in terms of the M.G.F. for just the y's, the untransformed y's. So let's just write down what the definition of this thing is. This is going to be e to the expectation of e to the sum of the yi's divided by square root n times t. So just applying our definition directly. I'm going to slightly change this to square root of n right here. So I didn't do anything except apply some braces. And I'll also point out that this thing right here is the expectation of the product. I goes from 1 to n e to the y i's times t divided by square root of n. So nothing fancy. So same exact thing. And then I can pull this product sign outside of the expectation. Somebody help me out. Why can I pull that product sign outside of the expectation? They're all independent. So everything factorizes. So this is the IID assumption. And I'll just write down that I don't need to actually index that because everything is identically distributed. So that's the other ID assumption. They're all exactly the same random variables. They might take on different values, but their properties are exactly the same. And so I can rewrite this thing as the expectation of EY t divided by square root of n powered up to the n power. So for IID stuff, I can just apply this transformation directly to M.G.F itself. And I can rewrite this down as the M.G.F for y, and I'm evaluating it with t square root of n. So anywhere I see a t in that moment generated function, I'm just going to divide it by square root of n. So these are exactly the same. So I guess applying this whole power to everything is I can write it down like this. So what we're actually going to do in our proof is show that this thing, y t over square root of n, raised to the nth power, we're going to prove as n goes to infinity that this is e to the t squared divided by 2. So, and recognize that is the M.G.F for a normal 0, 1. So that's where we're aiming towards. So let's see if we can prove that. So instead of taking the power and raising everything to n, I'm first just going to chisel away at the Taylor expansion on this function. And then we'll power it up to n once we get through the Taylor representation of that. And then we'll take the limit. So let's just look at this. My t over square root of n. I can Taylor expand everything if it's a smooth M.G.F. like this. Sum, k goes from 0 to infinity. M to the kth derivative. I need to center this somewhere. If I'm going to apply this, divided by k factorial, and then I'll just put in my polynomial terms. t over square root of n minus our centering parameter. Raise that to the k power. So I'm going to assume there's a polynomial representation of this M.G.F. If we're going to do this proof, we're going to have to pick some value to plug in right there. So what's the obvious value we should insert? 0. So we'll pick this at 0. Why would we center everything at 0? Is it just arbitrary? So we know in practice that Taylor expansions work different. They have different errors for different centering parameters. So the estimation is good around the centering parameter. So why would we center it at 0?
Derivative at 0 is just a mean.
That's true. So we could have some mathematical reason for doing it. Maybe it's easy to work through. So it's convenient for us. Jake?
Are we trying to show that it's a normal centered at 0?
Yeah, exactly. So the mass of the distribution, we already kind of know that it's centered at 0. Everything is standardized. So the approximation is good there. So we have a mathematically convenient reason, and then we have a practical reason for doing it. I like that. So I'm just going to substitute 0 in there. So that's a good choice. Okay, real quick, there's a few things we know. We know a few things about some of these terms. They're baked into our assumptions already. So real quickly, what's this? Centered at 0. So this means I'm taking no derivatives of everything. It's 1. So this is the expectation of e to the yt. Right here, where I'm going to plug in, I'm going to take the t is equal to 0. Right here, that's just expectation of e to the 0, expectation of 1, which is 1. So this is true for any distribution. It's basically just a statement that if you integrate the density function, it integrates to 1. That's true for all distributions. So no assumptions there. That's always true. So this is the first moment right here. Let's take this thing, plug in 0 right there. This is the expectation of y. So if I take one derivative, apply the chain rule, and do the thing that we do with moment-generating functions, i.e. generate the moments, I can say something about this first moment. We already know what this is. What's this one? This is 0. So just keep in mind, I took yi minus mu divided by sigma right here. So this is centered at 0, so the first moment is 0. So this is the second moment. Expectation y squared. So I can do this expectation of y all squared to recognize this. This is 0, so I'm just subtracting off some funny form of 0 in that, and then I recognize this to be the variance. So this is the variance of y. So the second moment is equivalent to the variance because it's centered at 0. So what's this? This is 1. So same reason. Okay, so we know a few things about these terms. So this is our finite variance assumption. We don't actually know anything about the other terms in the Taylor expansion. So we're going to apply this approximation to our moment generating function, and then we'll show that the remainder is actually converging to 0. So let me just rewrite this. This is going to look like this. I'll say 1 right here. So the first term is 1. So 0 factorial is 1. That thing is 1. When I power something up to the 0th power, I get 1 back. Our next term has the first moment in there. It's 0 divided by 1 factorial times t over root n raised to the first power, but I multiply by 0, it's still 0. This is my third term in the approximation, and we know something about its leading coefficient. It's going to be 1 divided by 2 factorial. So k is 2 there. T over root n raised to the second power. And so our limited assumptions that we've applied tells us that we know this first part of the Taylor expansion. And then there's going to be plus some remainder term. K goes from 3 to infinity. Moment generating function, k derivative of the moment generating function evaluated at 0 divided by k factorial. T over root n. I'll stop subtracting off the centering parameter because it's just 0 raised to the k power. So the remainder term starts at k is equal to 3. So this is what the book calls R, the remainder. Ry t over root n. So we'll give it some notation. We can already tell real quickly that as n goes to infinity, these terms right here, mk, I'll write it out explicitly. Let me just write down the remainder, and I'll plug in a few terms so we can just look at it. M, third derivative, centered at 0, divided by 3 factorial, t over root n, raised to the third power. We plug in a few more terms. Plus m4, centered at 0, divided by 4 factorial, t over root n, raised to the 4th power, so on and so forth. So what we notice real quickly is I always have an n down here in this. So it's raising it to the third power. As n goes to infinity, this thing is going towards 0. This is a constant, that's a constant. They don't depend on n. So no n's in there. Same thing happens right there. So this whole thing is going towards 0. So the remainder goes towards 0. Now I made a statement last time about Taylor's theorem. What Taylor actually said is Taylor said you only need to look at this first term right here and compare it to the highest order term in your approximation and make sure this is going to 0 faster than that thing right there. So the remainder converges to 0 faster than the approximation approximates the function. So if we're going to explicitly compare this term to the highest order term, we can compare it in a ratio sense. So Taylor tells us to look at the highest order term in our approximation and compare it to the lowest order term in our remainder. If you wanted to look at all the other terms in the remainder, I think that's okay. You could do that. You don't even need to know what Taylor said about this first term is what bounds everything, because these terms are going to 0 faster than that first term. And so we can convince ourselves of that real quickly because it's powered up to a higher power. So just note that our highest order term in our approximation is 1 over 2 factorial. I guess we could start calling that 2 pretty soon, so I'm just going to get rid of the factorial. This is going to be t over root n raised to the second power. So this is my highest order term in the approximation. And I'm going to compare it to this term right here. So m to the third power centered at 0 divided by 3 factorial. All this stuff is constant, so they don't matter in this, but we'll write it down anyway so we can see where everything comes from, times t over root n raised to the third power. So this thing looks like this. It's basically, if I take that square root of n, power it up to 2, that's an n down there, and I can kick it over to the top. So this is going to look like n times the remainder, essentially. T over root n. And what we can tell is this remainder, again, is bounded by this term right here. So this is going to be m3 centered at 0 divided by 3 factorial times t over root n to the third power. I guess I could get rid of the squiggly approximation sign and just bury it in 1/2 in there. It didn't really do anything for us. And then I have that t squared down here as well. So again, this has nothing to do with the limit. So as I take the limit of this, I can just see what happens. That n up there, that's always a linear term, and I always have a term in here that looks like n to the 3 halves. So there's an extra square root of n in there in the lowest order term in the remainder. And so this is converging to 0 faster than that one is getting big. So this goes to 0. So Taylor would say this approximation is probably pretty good. So the remainder isn't overwhelming the approximation. We'll use that. So here's what we're going to do. We're going to apply all this. So our M.G.F. for sum of the yi's divided by square root of n t. This is going to be equal to, again, the moment generating function for the y's, t over root n raised to the n power. And now we'll just substitute our Taylor approximation for that moment generating function. This will look like 1 plus, I'll get rid of this term, that's just 0, so we'll drop that, times, or plus, 1/2 t over root n squared plus the remainder term. So these are equivalent to each other. I'll just rewrite this again one more time. 1 plus t squared over n 1/2 plus the remainder. Raised to the nth power. I'll rewrite this one more time, just a little bit differently. Basically, what I think is okay is you could show that this thing we know as we take the limit, this is converging towards 0. I'm powering it up to the nth power, so if it's decaying towards 0, powering it up to the nth power doesn't change anything. It drives it down towards 0 faster. If you want to be a little bit more formal about this, you need to use Slutsky's theorem. So if you don't know what that is, I think it's okay. So I'm not going to test you on it. So let me just rewrite this. This is the formal way to deal with the remainder. This is just 1 plus t squared divided by 2. I'll write in the 1 over n right here, and I'll just write down n times the remainder. So I factorized out a factor of n here. T over root n. And this is going to be raised to the nth power. So again, I've just rewritten everything. No assumptions needed there. So I've already checked this thing. I know that that goes down towards 0. We check it here. So this is the treatment of Taylor's theorem and the treatment of the remainder and showing that that thing decays down towards 0. So we know that decays towards 0 because the approximation is good, which we just showed. Okay, there was a fact that I wrote on the board a little bit earlier, but I never said anything about it. Let me just rewrite it. So here's the fact. 1 plus a over n raised to the nth power. I take the limit of this. Some of us may know that that's e to the a. So sometimes that's taken as a definition. You could probably prove this using L'Hopital's rule, but we'll just recycle something that I think we all know. So in your first calculus class, they did this pretty early. Showed you this, and then they used it over and over again. Okay, we're going to do the same thing right here. So I have something that looks almost just like that, but I've also got this remainder term in here multiplied by n. So this thing, the whole thing, is going to converge to e to the t squared over 2 plus n, the remainder, t over root n. That's just true. I probably need to say something about this n right here. So I've already applied the limit, but what I really want to do is just multiply this thing by this, e to the n remainder t divided by root n, and then apply the limit again. Limit n goes to infinity, and then I can just show that this thing right here is converging towards 1. Because this thing is converging towards 0. That's actually the application of Slutsky's theorem, is I can apply this limit in 2 different steps. So if you know that, cool. If you don't know that, I would say just look in your book up. Slutsky's theorem. You can look that up. I've always taken this as a pretty obvious statement that limits do this. I guess if you took a measure theory class, they would probably want you to prove this statement, but it's something that seems so obvious that we're just going to skip over that. But it is in the book. I think it's in chapter 4. So if you want to just read that. I will not test you on this statement, but I do want you to just say something about this thing is going towards 0, and when I power it up to n, it's driving towards 0 even faster. So you need to tell us something about the remainder going towards 0. I think we've actually done a better job than the book actually did in showing this. They just apply Slutsky's directly and assume that we know it. And that's it. So that's the end, is that we've just shown what we set out to show. So that this moment generating function is e to the t squared divided by 2. So we just showed that that test statistic is normally distributed. Jake?
So you had said kind of, I think, Wednesday, that some of the way that you can treat the remainder in this class showing it goes towards 0, you can be a little bit looser with it than you would on a qualifying exam. Is citing the application of Slutsky's theorem what?
It's good enough for me.
Is that good enough for this class or good enough for the qualifying exam, good enough for both?
Good question. So if you just all of a sudden say, hey, remainder is going towards 0, I'm just going to say that and I'm going to remove this from the argument and just apply the limit directly. If you're an engineer or master's student in this class and you don't want to get a PhD in statistics, I would take that as an answer. I'd say, okay, you showed me that the remainder is driving towards 0. You wrote a sentence in that said, as I power it up to the nth power, it's driving towards 0 faster. I would be okay with that. For the PhD qualifying exam, I'd want you to show that n times that thing is going towards 0, apply Taylor's theorem to this, show me that that thing is driving down towards 0, and then you can throw it away after you say that. And apply Slutsky's theorem, and you can just cite it. I think that's okay. Okay, so just how delicately you treat the remainder, I think it just kind of shows your level of mathematics. So when you actually go to write theoretical papers, you'll want to say that. And your referees will take that as an answer. You cited Slutsky's theorem, it's well known, we can apply it correctly. So I'm not a measure theorist, so I like to apply statistics to actual data problems, so I'm not super concerned about this. Saying that, if you get somebody that is a measure theorist, they'll probably say, oh no, you need to prove that. They'll probably say you need to prove that the whole real number line is connected to. If you go all the way back to the axioms of counting. So we won't require you to do that. So basically we proved our statement. Central limit theorem holds. And it holds in even with less assumptions. But I won't ask you to prove that either. So here's a guarantee. I'm going to ask you to prove this at some point. So I would say go home, study this, and make sure you're able to do this. It's bound to appear on a final or a midterm. So it's one of those things. I think statisticians should have some proof of the CLT in their back pocket at any time. So when are you going to show that to people? I don't know. Maybe at your next party you go to or something. Any other questions about this? Okay. Homework's due today. So I like it the old-fashioned way where you just turn it in at the front. If you don't have it with you, you can turn it in under my office door. My office is 401A Hutchison. So if you haven't printed it out or you didn't put a staple in it, all those things that I've heard a million times, you still have time. Just slide it under my door. So if I see it there in the morning, it counts. So no big deal. I'm also going to present you with some new homework problems, so stay tuned for that. I'll put them up online later tonight. So you'll have some more homework problems to kick off, and we'll do another review session in a few days. Maybe in a couple weeks. Not this next week, but maybe the week after. Makes some sense. So I'll give you about 2 weeks to complete homework assignments. So nothing pending right now. Okay? Have a great weekend, you guys. Next week, we're going to cover the delta method, so if you want to get started on reading that, it's going to be a very similar proof to what we just did, and I'll have a lot to say about that. It's one of my least favorite methods to apply, but it's kind of an elegant proof. So I like talking about the mathematics, and then I basically will demonstrate later on in the class delta method doesn't work that way. So it's an old 1960s type of method. Okay, that's it, you guys.